Hello student, today I will teach you how to calculate total number of stereoisomer, active stereoisomer and inactive stereoisomer in a given molecule. So we will calculate for symmetrically substituted molecule and asymmetrically substituted molecule. Now for symmetrically substituted molecule with even number of chiral center. So first of all I am giving one example. Tartric acid, that is COOH, CHOH, CHOH, COOH. This is the formula of tartric acid. Now symmetrically substituted molecule. If terminal functional group are same, then it is known as the symmetrically substituted molecule. Here there will be two chiral center are present, right? Even number of chiral center with symmetrically substituted molecule. Next example we can write, suppose CH3 CHOH 4 times CH3. So this is the terminal functional group are same and there will be 4 chiral center. So even number of chiral center with symmetrically substituted molecule. Now for odd number of chiral center we can write this example, CHOH 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 COOH. So there will be two terminal COOH group which are same, so it is symmetrically substituted molecule, and there will be 3 chiral center, that is odd number of chiral center over here. Now asymmetrically substituted molecule, so we can give example COOH CHOH CHOH CH3, that is terminal functional group are different, right? So it is known as the asymmetrically substituted molecule. Now for symmetrically substituted molecule with even number of chiral center, so there is some formula for calculate total number of stereoisomer, in which how many number of active stereoisomer are present and a number of inactive stereoisomer are present. Now for symmetrically substituted molecule with even number of chiral center, so total number of stereoisomer is 2 raised to n minus 1 plus 2 raised to n minus 2 divided by 2, right? Where n is equal to number of chiral center. So here number of chiral center may be 2, 4, 6, 8, that is even number of chiral center are present. Now total stereoisomer, in which active stereoisomer are 2 raised to n minus 1 and inactive stereoisomer are n raised to 2 raised to n minus 2 divided by 2, right? So this is the formula for total number of stereoisomer for symmetrically substituted molecule having even number of chiral center. Now for odd number of chiral center, and if molecule is symmetrically substituted, so total number of stereoisomer is 2 raised to n minus 1. Number of inactive stereoisomer is 2 raised to n minus 1 divided by 2, right? And number of active stereoisomer is total number of stereoisomer, that is 2n raised to minus 1 minus number of inactive stereoisomer, that is 2 raised to n minus 1 divided by 2, right? So this is the formula for this one. So here you can remember there will be even number of chiral centers, so n minus 2 divided by 2. Here odd number of stereoisomer, so odd, that is 1, so we can write over here n minus 1 divided by 2, right? So now next, by using this formula we can calculate by giving some example. So for asymmetrically substituted molecule, we can tell the equation is 2 raised to n, right? So n is equal to number of chiral center. Now next, for symmetrically substituted molecule with even number of chiral center. So here the example is given: tartric acid COOH, CHOH, CHOH, COOH, right? So there is 2 chiral center is present, so n is equal to 2, right? Now number of active stereoisomer is 2 raised to n minus 1. Number of inactive stereoisomer 2 raised to n minus 2 divided by 2, and total is 2 raised to n minus 1 plus 2 raised to n minus 2 divided by 2, right? So by putting the value 2, here we can write 2 raised to 2 minus 1, that is 2, and by putting 2 value we can write 2 raised to minus 2 divided by 2, that is 2 raised to 0 by 2, that is 2 raised to 0, that is 1. That is, we can say number of active stereoisomer is 2, number of inactive stereoisomer is 1. So total stereoisomer is 2 plus 1, that is 3. So inactive stereoisomer, that is optically inactive stereoisomer, right? So there will be plane of symmetry present over there. So we can say it may be meso compound. So here we can give example. Suppose COOH, right? First example is this one. Okay, so there is plane of symmetry is present over here, right? So this is optically inactive. It is optically inactive, and there is 2 chiral center, so it is meso compound. So what mean by the meso compound? It is optically inactive, it has presence of plane of symmetry, and minimum there will be 2 chiral center is present, that is known as the meso compound. So here we can say one meso compound present over here. Now optically active stereoisomer are 2. So we can say that COOH. Suppose I change the position of OH over here, hydrogen and hydrogen. So this is the optically active stereoisomer. Suppose I draw the mirror image of this one, right? So COOH, OH, hydrogen, OH, and COOH, right? So these both are enantiomer, and we can say that that is racemic mixture, or they are optically active. So there will be 2 optically active stereoisomer present over here. Okay, now suppose we assign the Rns configuration. Suppose I am this is 1 number, 2 number, 3 and 4, right? So 2 number and 3 number are chiral center. So suppose I find Rns nomenclature. So we can say that for 2 number carbon, right, this is 1 number, this is 2 number, because this is 2 number, and this is 3 number, and this is the 4 number, right? So we can say 1, 2, 2, 2, 3 anti-clockwise, so S configuration, so 2S, but hydrogen present over here, so 2S become 2R, right? So same for this one, for 3 number carbon, if we calculate, then we can say OH has given first priority, COH is second priority, and this is the third priority, this is the fourth priority. So 1, 2, 2, 2, 3 clockwise, so R configuration. So we can say that 3R, but hydrogen present over here, so 3R become 3S, right? So here configuration of meso compound over here is 2R 3S, right? Now next for this carbon, 2 number carbon and 3 number carbon. So 2 number carbon position of OH is over right hand side. So whatever the configuration in structure 1, that is the configuration in structure 2, right? So 2R. Now for 3, position of OH is changed. So R become S. So sorry, S become R. So 2R 3R, right? Now see, this third molecule is enantiomer of second molecule, so it has configuration exact opposite of this one. So 2R 3R, so we can say its configuration is 2S 3S, right? So here one optically inactive, that is meso compound is present, and optically two optically active, that is enantiomer are present over here. So total there will be 3 stereoisomer are present. Now next one, for this example, here example is given COOH, CHOH, 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 CHOH and COOH. So there will be total 4 stereoisomer are present. Sorry, 4 Keral center are present. So we can write N is equal to 4. Now optically active stereoisomer 2 raised to n minus 1, inactive 2 raised to n minus 2 divided by 2, and total 2 raised to n minus 1 plus 2 raised to n minus 2 divided by 2, because this is the symmetrically substituted molecule and even number of Keral center. So we can write by this equation, by this formula. Now by putting value 2 raised to 4 minus 1, so total 8 active stereoisomer are present over here. So total 2 inactive stereoisomer are present, and total stereoisomer are 10, right? So we can say there will be 2 meso compound optically inactive, and there will be 4 molecule which and enantiomer of there, that is total 8 molecule which are the optically active stereoisomer. Now first of all I will draw optically inactive stereoisomer, that is meso compound. Okay, so I am putting COOH, COOH. So meso compound has plane of symmetry, right? And so suppose I draw the plane of symmetry, and it is optically inactive. So suppose I am writing over here OH, OH, OH and OH, right? This must be hydrogen. So here plane of symmetry and minimum 2 Keral center. So here we can say there will be 4 Keral center. So this is the meso compound, and it is optically inactive. Now second meso compound. So for meso compound there must be plane of symmetry. So see, suppose I put OH over here, so I can put OH over here. Suppose I put OH over here, then OH over here, right? So this is the second meso compound, and it is also optically inactive, right? If I find electronic configuration at second, third, fourth and fifth carbon, then it has it has configuration 2R, 3R, 4S, 5S, right? And here 2S, 3R, 4S and we can say 5R, right? So 2 meso compound, that is optically inactive stereoisomer are present. Now optically active stereoisomer. Okay, so firstly COOH, COOH, right? Okay, now suppose I put over here OH, OH, OH and OH. I'm not writing hydrogen in any molecule, okay? So you have to understand yourself. Okay, so now configuration. So firstly, 2 number carbon, this is 3 number, 4 and 5th. If I found uh, then 2s, 3s, 4s and 5s, this molecule has this configuration. Now mirror image of this one, so COOH, COOH. So here we can write OH, OH, OH and OH. So this second molecule is mirror image of first one, so its configuration is exact opposite of first one. So 2s become 2r, 3s become 3r, 4s become 4r and 5s become 5r, right? Okay, now third molecule COOH, COOH, right? Okay, suppose I change the position at carbon number 3. Suppose, sorry, I change the position at carbon number 4. Suppose I change 4 number carbon from first one. We are comparing with first one. So OH, OH, OH and OH. I change the position at carbon number 5. Sorry, carbon number 5. This is the carbon number 5. Okay, so its configuration only change at carbon number 5. So we can write 2s as it is, 3s as it is, 4s as it is. Now at 5 number, in first molecule there will be 5s. So here we are writing 5r because change the position at only carbon number 5. Now next mirror image of this third molecule COOH, COOH, OH, OH, OH and OH. The fourth molecule is mirror image of third molecule. So it has exact opposite configuration to third one. So 2s become 2r, 3s become 3r, 4s become 4r and 5r become 5s, right? So we have to only firstly find the configuration for only one molecule, and then from one molecule you can find another molecule also. Now next one, now fourth molecule COOH, COOH, right? Okay, suppose I change the position at carbon number 4 only. Here I change the position at carbon number 5. So here 4 compared to first molecule. So I am writing OH, OH. So here in first molecule left hand side, so I am writing here OH right hand side. So change in configuration only at fourth number carbon. So 2s as it is, 3s as it is, so 4s become 4r and 5s as it is, right? Now mirror image of this molecule, fifth molecule. So exact opposite to fifth molecule, 2r, 3r, 4s and 5r, right? Okay, now suppose I change the position at carbon number 3 and carbon number 4, COH, COOH. So OH, now carbon number 3, so compared to molecule 1, it become left hand side. Carbon number 4, so it become right hand side. Okay, so change the position, change the configuration at 3 and 4 only. So 2s as it is, 3s become 3r, 4s become 4r and 5s as it is. Now enantiomer of this seventh molecule, so we can write over here So exact opposite configuration to seventh molecule, because both are enantiomer. So 2s become 2r, 3s become 3r become 3s, 4r become 4s, and 5s become 5r. Okay, so here we can say there will be total 8 optically active stereoisomer are present in a symmetrically substituted molecule having even number of chiral center. Now symmetrically substituted molecule with odd number of chiral center, right? Okay, so first of all we will calculate optically inactive stereoisomer, total stereoisomer. Total stereoisomer is equal to 2 raised to n minus 1 optically inactive stereoisomer, that is we can say 2 raised to n minus 1 divided by 2, and optically active stereoisomer, that is total stereoisomer minus optically inactive stereoisomer. Here in this case, here COOH, CHOH, CHOH, CHOH. So there will be 1, 2 and 3. Total 3 chiral center are present. So we can write over here n is equal to 3. So by putting value 3, 2 raised to 3, that is 2 raised to 2 raised to 2, that is 4. So total 4 stereoisomer are present, in which optically inactive 2 raised to 3, 3 minus 1, that is 3 minus 1 divided by 2, that is 2 raised to 2, that is 2 raised to 1, in which 2 are optically inactive, and total stereoisomer are 4, inactive are 2, and 2 are optically active. That is we can say there is 2 optically active and 2 optically inactive stereoisomer. That is we can say there will be 2 meso compound and 2 optically active stereoisomer. Okay, so firstly I write down to, first of all COOH, right? COOH. So firstly I write down the meso compound COOH and COOH. So meso compound, suppose I write OH, OH and OH. So there is the plane of symmetry present, right? And we can say the at least there will be at least 2 chiral center are present, and it is optically inactive. So this is the meso compound. If I assign the configuration, then we can say this molecule, this chiral carbon 2 number, this is 3 number, and this is the 4 number. 2 number chiral center has R configuration and 4 chiral has S configuration. So suppose I want to find out the R or S at 3 number carbon, then we know that R has more priority than S, right? So we can say that if we assign R or S configuration at carbon number 3, then it becomes R. So 2R and 4S and 3 small r. It is denoted by small r. What mean by the small r? This is known as the pseudo chiral carbon. Pseudo chiral carbon. So we can say constitutively the carbon number 3 is same, but configurationally both are different. Suppose if we constitutionally we can say that both have same functional group, but configurationally this both are different. So it is known as the pseudo chiral carbon. Next meso compound C, we can write COOH, COOH. OH, OH and OH. Okay, so plane of symmetry passes from this one, right? So this is same, so we can assign configuration. So it has R configuration and it has S configuration. Okay, so suppose for this is carbon number 2, 3 and 4. Now for carbon number 3, if we want to find out R or S, so this is given one number, right? And R has more priority than S, so this is given 2 number and this is given 3 number. So 1 2 2 2 3, that is clockwise, so it is R, but hydrogen present over here, so R become S, right? So 2 we can say 3 R become 3S. This is also known as the pseudo chiral carbon, right? So its configuration 2R as it is, 3S small s, for chirality small r, pseudo chirality small r and small s will be used, and 4S. Later on after this video I will explain in detail pseudo chirality, right? Now next one is this both molecule are optically inactive because there will be two meso compound are present. Now next one OH, OH and OH, right? Now its configuration is 2R and 4R. So see, carbon number 2, this is 3, this is the 4. Now for 2 carbon number 2, the configuration is R, and carbon number 4 configuration is R, right? So this is achiral carbon, this is the achiral carbon, because we can't find R or S over here because both have same configuration, right? Constitutionally both are same as well as configurationally both are same, so it is achiral carbon. So just I only write 3, we can't assign R or S. Now next one, enantiomer of this one, so COOH, COOH, OH, OH, OH. So second molecule is enantiomer of first one, so configuration is exact opposite of first one. So 2R become 2S and 4R become 4S. So this is the S, this is the S. So this is also known as the achiral carbon because we can't find R and S over here. So just we only write 3, right? So here there will be two optically active stereoisomer, that is first and second, and optically inactive isomer 2, that is 3 and 4, and both are meso compound. Okay, and in meso compound there will be central carbon, that is known as the pseudo chiral carbon because around central carbon both functional group are constitutionally same but they are configurationally different. Now next one is for asymmetrically substituted molecule. The molecule is given CH3, CHOH, sorry, here suppose I am writing CH2, right? CHOH, COOH. Okay, now this is the asymmetrically substituted molecule because terminal functional group are different. Okay, now we know that total number of stereoisomer are 2 raised to n, that is 2 raised to there is 2 chiral center, the 4 chiral center are present. Okay, so firstly one by one, so this is the COOH and CH3, right? Suppose I put over here OH and OH, right? Okay, so this is not meso compound. Consider in symmetrically molecule there is meso compound, this is not meso compound because plane of symmetry is not present. This COH group and methyl group both are different. So this is not optically inactive stereoisomer, right? We can say it is optically active stereoisomer because there is no plane of symmetry, right? Okay, suppose we assign configuration at carbon number 2 and carbon number 3, right? So carbon number 2, we can say that OH group is on right hand side. So first of all given number 1 priority, after then COH has given number 2, then CH this is 4, and this is the hydrogen, so this is given 4 number. So 1 2 2 2 3 anti-clockwise, so S, but it is hydrogen present horizontal, so it is R. So we can say 2 R present over here, and for this one, this molecule, this carbon, 3 carbon, one number is given to this one, right? Second number is given to this one, and third is this one, fourth is this one. So 1 2 2 2 3 anti-clockwise, so S, but S become R over here, so 2 R 3 S, right? Okay, now next, suppose I take enantiomer of this one, COOH, mirror image of this one. So I am writing over here OH, OH, hydrogen, hydrogen, and methyl. So configuration is exact opposite to first one. So 2S and 3R, right? After then, suppose I change the position of OH, COH, CH3. At second number, third number carbon, if I change the position, right, then we can calculate, we can tell. So this has same configuration as 2R, while 3 carbon has OH in left hand side, so 3S become 3R, right? Now mirror image of this one, COOH, OH, OH, CH3. So configuration is exact opposite to this one, so 2S, 3S, right? So here we can say there are total 4 stereoisomers are present in a molecule which is asymmetrically substituted. So thank you very much. In next video I will explain you about pseudo-chirality. So note that pseudo-chirality is observed in a symmetrically substituted molecule with odd number of chiral center. Thank you very much.